Hello everyone, I'm back with the part 2 of my final presentation. So my part 2 is from the part 4 of my final report. And coming to the part 4, the first question is about the vanishing gradient problem. What is vanishing gradient problem? Okay, vanishing gradient problem refers to a case where the gradients of a loss function calculated during the gradient descent procedure get extremely small or close to zero in direction of the updated weights. Thus, as we using the gradients are multiplied through different multiple layers of the network tend to decrease exponentially, which makes the weight not to be updated anymore. The problem is further exaggerated in RNNs since the recurrent connection is involved in which the same weights are used to process the information sequence. The more to sequence cost is, the smaller the gradients are. In particular, the gradients in the earlier part of time steps are both small and difficult to learn and transfer. The vanishing gradient issue causes uh, slow and even static learning process. Because of small values of a weight reduce the angle of the weight so that the model fails to capture long-term information in the data sequence. So coming to the exploding gradient problem. Okay, the polarization of gradient problem goes along the opposite direction of gradient problems, that is bound to zero similarity degree to each other. For this reason, gradients of the chain rule of the loss function with gradient with respect of weights dramatically increases during the backtracking. The most essential thing to focus on here is that sometimes it could happen that the weights are corrected with the extreme values, which finally causes divergence or instability in the learning process seen to the size of gradient. So the recurrent multiplication of gradient can lead to the same vanishing gradient and exploding gradient problems in RNN, as it occurs usually in the other models. If the gradient of the function is too steep, the weights update can get far from their start point and grow exponentially, thus creating numerical instability leading to the problem with model convergence. The problem of the vanishing and the exploding gradient can bring significant difficulty of learning in deep neural networks, especially in some situations where sequential data needs to be captured, such as natural language processing, speech recognition, and time series forecasting. Coming to the Coming to the question number 2 in the part 4 about the limitations of simple RNN neural network. Simple RNN or plain RNN is a simple architecture of RNN having few drawbacks which reduce its applicability of sequence data in certain tasks. These limitations include inability to capture long-term dependencies. In the previous question, the issue of vanishing gradient of simple RNNs was covered. As a result, it turns out that these neural networks have difficulties with learning and remembering long-term patterns in sequential data. With the increasing sequence length, these gradients will be smaller and smaller. Hence it will become difficult for the networks to effectively learn as well as propagate data from the initial sequence steps. And another limitation is limited memory capability. Simple RNNs have extremely narrow memory bandwidth, which is due to the fact that the memory is then consists of only the hidden states. The fact that this hidden states is always replaced with a newer version at each time step causes it to be rendered untrackable, thus making it impossible to retrieve information from the earlier time steps required for longer sequence. And another limitation is sensitivity to input perturbation. Minor changes in the information fed to the simple RNN can dramatically change its hidden state and hence will produce unstable and unreliable behavior. This might be one reason why it is hard to handle the degree of noisy or non-linear input sequence collectively. And there are other limitations such as difficulty in handling complex data and lack of parallelization. This is because simple RNNs cannot process long sequence and cannot capture uh, complex dependencies, resulting in the fact that they are not the most favorable for long-range dependencies task. And another question in the part 4 is explaining how the LSTM neural network can provide robust solution to the gradient problem, like vanishing gradient problem and exploding gradient problem, and addressing the limitations of simple RNA. Okay. So LSTM, long short term memory neural network architecture, which is richer in functionality than simple RNN, was introduced to overcome the vanishing and exploding gradient problem that simple RNN have, as well as to improve the inability to capture the long-term dependencies in the data sequence. Addressing the gradient problem, LSTM make a gating mechanism and cell structure to advantage the computation, thus averting a gradient vanishing or exploding problem. The key component of a LSTM cells are the key component are the cell state, gates, and the forget gate, the output gate. The gates and cell states here play the important role in the selection of which information will be retained or forgotten at the time steps that are previous to the current one. So the LSTM is about the short-term memory. This role is performed such as LSTM. This mechanism is capable of addressing the vanishing gradient and exploding gradient issues simultaneously, since it will prevent existence of gradients that are too small or too large during the computation. So these are the LSTM addresses the limitations of simple RNN, such as capturing long-term dependencies and increased memory capability, and further robustness to per input perturbation and handling complex data and potential for parallelization. These are the figures which are the first one illustrate the LSTM. It has the input. This one is the simple RNN. Simple RNN has the input, simple RNN output, or it's like a sequential. So this is the LSTM, the advanced one, which has the forget gate, input gate, output gate, and multiple states. This is the vanishing gradient problem. And this is the exploding gradient problem. Coming to the part 5, it is about an LSTM neural which was designed to predict the CO sensor values from the air quality dataset. Our network design was made up of one LSTM layer having 64 neurons, which was followed by a dropout layer that had a regularizing rate of 0.2, and final output was a simple dense layer. The point of processing through string replacement and subsequently dropping row, which contained NaN, is the target variable was to ensure the data was clean. So coming to the coding part, this is the coding part of our part 5. Here in the step 1, it is first we have uploaded the data set and we did the data cleaning process by splitting the single column into multiple column, assigning the column names, Drop the first row which contained the column name, select the target variable, replace empty string with NaN, drop rows with NaN value, process data. This is the data cleaning process, and this is our attributes. Then this is the splitting the data into training and testing. Then this is prepare the data for LSTM, long short-term memory neural network. This is the design for LSTM network, and this is the training the model. Here we did the 100 epochs, and evaluating the model for test data. So the total loss is 0.002360, and retrain the model on the entire data. This is the forecast visualizing the result. So this is the result of our LSTM neural network. So a result demonstrate the model's accuracy in predicting the CO sensor readings. The forecasted value did follow the general trend of actual data, but there were some variations, especially in capturing the peak and valleys precisely. Therefore, it is frequent weakness of LSTM networks when processing the complex time series data. Coming to the part 6, it is about the redesigning the neural network. It is outcoming the limitations of the part 5. So this is the final visualization, but coming to the coding part. Again, first we have uploaded the data and we did all the data cleaning process, reprocessing the data, splitting the data into training and testing, prepare the data for LSTM, and then training the data, evaluating the model, and retraining the data, visualization. Here the suggested proposals are: the percentage of data for testing is increased to 25. LSTM layer added an additional LSTM layer with 100 neurons each. Dropout layers adjusted dropout rate to 30% to combat potential overfitting. Input sequence length increased to 48 to capture more temporal dependencies. Batch size reduced to 16 for more frequent updates during training. Training epochs increased to 150 to allow the network more iteration to learn the patterns. Okay, so these are what are the steps we have taken to overcome the limitations in the previous part 5. So this is our output. This is our data visualization, final data visualization. Here the test loss is 0.0025 and test loss for part 6 is 0.0024. So there is a reduce in the loss. These are the comparison of the part 5 and the part 6. From the visualization of LSTM, neural network adapted successfully and offers improved predictive capability for the carbon monoxide sensor reading from the air quality dataset. It seems that the forecasted values have a tendency to resemble the general trend of the actual data to a great extent relative to the previous model choice. Nevertheless, the regularity in the time series data still occurs, but in most cases, these deviations are significant and considerable. The model is affected by so-called tail phenomenon when forecasting extreme values. It often underestimates peaks and overestimate valleys. That is another explanation of various time series exhibited could be the variation of series pattern or the presence of irregular data points without clear and obvious trends. Regardless of tired renovations in the network architecture, our newly styled data models still may be called into the question for the shortcoming and the simplistic feature, which do not allow to grasp more complicated trajectories and the long-term association in the dataset. To further improve the forecasting accuracies, increment the LSTM layer or node numbers so that the number of network can uh, this Okay, and learn intricate representation. So these are all the steps that we have already discussed over here about the testing and training data set in the 25 and 75, and adding a additional LSTM layer to 100 neurals, and adjusted dropout rate to 30% to combat potential overfitting, and increased input sequential length to 48 to capture more temporal dependencies, reduced to 16 for more frequent updates during training, and epoxy is increased to 150. These are all the steps that we have taken. This is about those steps only. Thank you. This is about the part 2 of my presentation videos.